reconstructing words from right-bounded block words.
Okay, thank you, Nared, and thank you for giving me the opportunity to present our work. So this is a joint work with Pamela Fleischmann, Florine Manea, Dirk Novotka, and Michel Rigaud. And just before starting, maybe I'm going to mention that I can see the chat during the talk. So if you have any question, just write it. And so I'm going to study a variant of the classical reconstruction. Yes, a hand is just raised. I don't know if there is a question. Okay, so I'm gonna present a variant of the classical reconstruction problem on words, and I'm gonna give the results that we obtained first on binary alphabets and then on a classical arbitrary large alphabet. So let us start with some background. So we are going to consider finite words that are just finite sequences of elements called letters that come from a finite set that is called the alphabet, denoted by the letter A. And we're going to consider subwords, which are subsequences of a sequence of letters building a word. And this subsequence does not have to be contiguous. So for example, in the word ABCBABA, ACA is a subword. And we denote by the binomial coefficient UV the number of times that V occurs as a subword in U. So for example, in ABCBABA, I can see the subword ACA 2 times because I have only one occurrence of C, so I'm obliged to take this C. I only have one occurrence of A before the C, but then I have 2 occurrences of A before the after the C, so I have 2 occurrences of ACA as a subword. Okay, and let's start the reconstruction problem with an example. Let's take a binary alphabet and a word U of length 6 that we don't know, but we have some information about it. So first, we know that it's of length 6, and we know that it has 3 occurrences of A and 7 occurrences of AB. And the question is, can you uniquely determine U? So let's start to do it quite simply. So first, I cannot put all the B's before the first A, because otherwise I won't have any occurrence of AB. I cannot put all the B's somewhere before the second A, because otherwise I will have at most 3 occurrences of AB, and the 3 occurrences appear if I put all the B's rightmost before the second A. For the same reason, I cannot put all the B's before the last A, so I have to put at least 1 occurrence of B after the last A. And this B will contribute for 3 occurrences of AB. So I continue, I'm sure that I have a B here. Then I cannot put a second B before the first A, because this B won't contribute for any occurrence of AB. So I have to put a B at least here. And if I put 1 B here, this B will contribute for 1 occurrence of AB. And so 3 occurrences are remaining, and the last B has to be here. But in place of this B, I could have put it here. And so this B contributes for 2 occurrences of AB, and the last B has to be put here. And I have a second word that satisfies the 2 conditions. So we cannot uniquely determine the word U from these 2 conditions. But if I add a third condition, I know that the number of AAB as a subword of U is 5. Then I can determine the word U uniquely, because I had 2 possibilities and only one of them is satisfying the third condition. Okay, so what is the classical reconstruction problem? In fact, we have a finite word. I need a definition first. So I'm gonna speak about K deck of a word U, and the K deck is just the multiset of all the subwords of U of length K. So for example, the word AABBAB, we are gonna look at all the subwords of this word of length 3, and we are counting them with their multiplicity. So for example, AAB occurs 5 times in this word. So this is the K-deck of a word U, and it always has the same cardinality. It's the classical binomial coefficient. And so the classical reconstruction problem, if we have an alphabet and an integer n, we are interested in the minimal integer k, such that any word of length n can be uniquely determined from its k-deck. And our variant of the problem is the following. So we are going to ask questions of the type, what is the value of the binomial coefficient uv? But what changed is that we are gonna ask these questions sequentially. So if we have an alphabet and an integer n, we have an unknown word of length n, and we are gonna ask question, what is the binomial coefficient of u v1? So how many occurrences of v1 can I see as a subword in u? How many occurrences of v2 can I see as a subword in u? Up to how many occurrences of vk can I see in U? And I want to ask the less questions possible. And I ask this question sequentially. It means that when I have the answers to the first questions, I can use them to ask the next question. For example, if I ask for the number of B's in a word and the answer is 0, I know that there are no B in the word, so I'm not going to ask the number of AB, for example. Okay, so let's start with a short survey of the results already known. And then let's look at our variant, the binary case first, and then the arbitrary case. Okay, so the reconstruction problem can be more general than just applied on words. And it's stated as follows. If I have sufficient amount of information about a hidden structure that is, a hidden structure, so sorry, I have a hidden structure that I don't know, but I have information about substructures of this structure. So for example, I have information about subwords of a hidden word. And can I uniquely determine the structure? So for example, about square matrices, it is known from Manvel and Stockmeyer that a square matrix of length at least 5 can be reconstructed uniquely from its principal minors given in any order. We could also ask a question about graphs. So if you take a graph with n vertices, you can consider all its subgraphs obtained by deleting exactly one vertex. So you obtain a multiset of subgraphs. And if two graphs have the same multiset of subgraphs, they are called hypomorphic. And Kelly and Ulam's conjecture states that two hypomorphic graphs with at least 3 vertices, they are isomorphic. And there is a similar conjecture by Harari about edge deleting subgraphs. And these two conjectures are still open, but already known to be true in some particular families of graphs. And obviously, you can ask the question about words from their subwords. And as far as I know, this problem was first stated by Kalashnik in 1973. Okay, so about the problem of reconstructing a word more especially. In fact, the problem is the following. You want to determine the function mapping to every natural number n, the minimal k, such that any word of length n is uniquely reconstructed from its k deck. So we want to determine the function. And some partial results were already obtained. So first, in 1975, Suchenberger and Simon, they showed that any word of length n is uniquely reconstructed from its k deck if k is at least half of the length of the word. Then it was improved by Krasikov and Roditi in 1997, and the bound is now in square root of n. Sorry. And another important result is by Dudik and Schulman, and they gave a lower bound. So they just say that k is at least this value. but there is still a gap, sorry, between these two values, so the minimal and the maximal, the upper and the lower bound. And there are probably a lot of other results that I don't especially know, but this problem is quite popular. Okay, so let's look at some interesting properties of the K-deck. So knowing the K-deck means that you know the binomial coefficients UV for every word V of length exactly K. Oh, sorry. Oh, wait, sorry. Okay. Oops. But in fact, if you know the K-deck of a word, you know the binomial coefficient of every word V, not only of length K, but of length up to K. How is it? So first, from the K-deck of a word, you know it's one deck. Because if you know the K-deck, you know the number of occurrences of K times in the word. And seeing the subword K times, you can see it exactly the number of ways of choosing K letters A among the number of letters A in the word U. So the one deck is known from the K-deck. And also the K minus one deck is known for the K-deck. And how can we see that? It's because of this quite ugly formula. So let's look at the formula on an example. If I have a word U and I want to compute two binomial coefficients independently. So I want to look at the number of occurrences of AB, AC and the number of occurrences of A independently. So first I can put the letter A, which is of the second coefficient, in all possible places in the middle of the first word ABAC. That gives the 5 first terms. But I can also merge the letter of the second coefficient with the same letter in the first coefficient. So I have this coefficient 2 times since there are 2 occurrences of the letter A in the first word. So this formula can be proved more formally, but this is the idea. And then you can isolate the binomial coefficient ux. And so if you have a word x of length k minus 1, you can use the formula and you can know it from what? From the one deck of u and from the k deck of u, because this word is of length k. So by induction, from the k deck, you know all the previous decks, right? Okay, and knowing the whole K deck is quite complicated because you need to ask a lot of questions of the type QUV, which means you need to ask how many occurrences of V can I see as in U as a subword, and you need to ask this question for every word of length exactly K. So you need to ask this number of questions. But we have an important result from Rottenauer that says that, in fact, some binomial coefficients can be deducted from other ones. And in fact, it suffices to have the answer sorry, to these questions for Linden words only. So just to recall, if I have a total order on the letters of my alphabet, a word is Linden if for any factorization of it into 2 non-empty words, I have that the word is lexicographically smaller than its conjugate. And how is it that it's sufficient to ask questions for Linden words? Let's look at the result. I need 2 definitions that you probably already know. Here are the formal definition, but let's maybe just look at the example. So the shuffle of 2 words is just the multiset containing all the words that I can obtain by shuffling the letters of the first and the second word. So for example, if I take the red word AB and the blue word AAB, I'm gonna shuffle the letters in all possible ways, but keeping the order AB here and keeping the order AAB here. So I can put AB before AAB, or I can put the B in the middle of AAB here, or at the end, and so on. And I'm gonna shuffle the 2 words like that, and I obtain a multiset. I also need the infiltration of two words. That's more or less like the shuffle, but I can merge part of the first word with part of the second word. So for example, if I want to take the infiltration of these two words, first I take the shuffle that you can see in red, or I can merge the first letter A with the first letter A and then shuffle B with AB. And I'm gonna obtain this word, and this word a second time by shuffling B with AB. I can also merge this A with this A, and then I need to shuffle A, which has to be before the common A, with BB, which has to be after the common A, and I obtain some words here. I can also merge B with B and shuffle A with AA. And I can also merge more than just one letter. I can merge AB with AB, and I obtain the word AAB. So these two definitions, the shuffle and the infiltration, are useful to understand why knowing binomial coefficients of Linden words is enough. So let's look at this small result. If I have a word that is non-Linden, I can always find a factorization of this word into two non-empty words, such that in the shuffle of the factorization, every word will be less than V or equal to V for the lexicographical order. And due to that, I have the interesting result here. If I want to compute a binomial coefficient UV, and if V is not non-Linden, I use the result of Rothenauer, and I say that I can take X and Y as in the previous proposition. And I have this formula. So I compute 1 over the multiplicity of V in the shuffle of X and Y. And then I have to compute the binomial coefficient of X, of Y. And then I'm looking at all the words that appear in the infiltration of X and Y. I count them with the multiplicity and I compute the binomial coefficient. And you can note that if you look at the radix order, so just to recall, the radix order is the following: X is smaller than V if either X is smaller than V in length, or they have the same length, but then X is smaller than V for the lexicographical order. So if you look at this order, all the words that appear here, X, Y, and W, for all the W of the infiltration, all these words are smaller for the radix order, smaller than V. Okay, this is just because of this proposition and the choice of X and Y. So what can you do? Maybe all these coefficients won't involve Linden words, but you can apply the formula recursively on all the non-Linden words that remain, because you know that they are smaller for the radix order, so the process is finite. So let's do an example. Let's take V, that is AB, AAB. This is not a non-Linden word, so I can find X and Y such that in the shuffle, all the words are smaller or equal for the lexicographical order. And this is the example we just did 2 slides before. So now I recall the formula, and if I want to compute the binomial coefficient UV with this V, I'm going to look at the multiplicity of V in the shuffle. V is here, its multiplicity is 1. Then the binomial coefficient of X and of Y. And then I'm going to look at all the words of the infiltration with the multiplicity. So 3 times this binomial coefficient, 6 times this binomial coefficient, and so on. And if I look at my formula, this word, ABAB, is the only non-Linden word. And so I could do the same on this word, find a new X, a new Y, and write the formula and inject inside it. And at the end, I will have an expression of this binomial coefficient involving only binomial coefficient for Linden words. So just to sum up, if I know the K deck, I know all the previous decks. So I can ask this number of questions. But in fact, if I know all the binomial coefficients of Linden words of length up to k, I know all the k deck, and so all the previous one. And how many Linden words of length up to k do I have? I have this quantity, where here this mu is the Möbius function. And this is really less. There are really few Linden words compared to this quantity. But just it's important to notice that I really need the binomial coefficients for all Linden words of length up to k and not exactly k. It doesn't suffice. For example, these two words, if I know all the binomial coefficients for Linden words of length exactly 3, I have only two Linden words of length exactly 3. I have AAB and I have ABB. So they have the same binomial coefficients for Linden words of length exactly 3, but then there is a Linden word of length 2, and the two words do not have the same binomial coefficient. Okay, so I wanted to show you why we consider this variant of the classical reconstruction problem. We really want to reduce the number of binomial coefficients computed. For the k deck, we needed to compute a lot of binomial coefficients, even using only Linden words. As I said before, if I know that a binomial coefficient equals 0, I won't ask a question where the word v involves the word w as a subword, because I know that the answer will still be 0. And the second motivation is that we don't want to restrict all our questions to words having the same length. Okay, so maybe let's go for the binary case. So, and let's start with an example to understand the algorithm, which is quite simple in the binary case. We have a word u that we don't know, and this word is of length 10. We are going to ask questions one after the other. So maybe the first question is asking how many A's or how many B's we have in the word. I'm going to ask for the number of B's, and the answer is 6. So since I have 6 B's in the word, I have 4 A's. I have less A's than B's, so I decide to write U in the following way. I'm going to put all the A's, and I'm going to put B's between all the A's. I don't know how many of them, so there are unknowns here. But I know that I have 6 B's in the word, so the sum of all these exponents is equal to 6. Then the next question, I won't ask for the number of A's because I already deduced that. So I can ask for the number of AB's, and the answer is 4. So I'm gonna write the following equation. I'm gonna look back at this form of U, and I'm gonna consider first these B's. These B's won't contribute for any occurrence of AB. These B's will contribute for one occurrence of AB because there was one A before. So I have S2. These B's will consider for 2 occurrences of AB. There are 2A before. So 2S3. And so on, 3S4, 4S5. And this quantity equals the total number of AB's, which is 4. So if I want to solve the equation, I have 5 solutions for the equation, S2, S3, S4, S5. And then S1 is deduced from the first equation. But I still have 5 possible answers, so the word is not uniquely determined. And I need to ask another question. I won't ask for the number of AA or the number of BBs because I can deduce it from that. I won't ask for the number of BAs because BA is non-Linden, so I can deduce it from Linden words AB, A, and B. So I'm gonna consider, for example, the word AAB. I'm gonna ask the question, and there are 2 occurrences of AAB. I'm going to consider this form again. These B's and these B's won't contribute for any occurrence of AAB. So these Bs will consider from one occurrence for AAB. So S3 is here. These Bs will contribute for 3 occurrences of AAB. Why 3? Because there are 3 A's before. So I have 3 ways of choosing 2 Bs among these 3, of choosing 2 A's, sorry, among these 3 A's. And these Bs have 6 ways of contributing because there are 4 A's before and there are 6 ways of choosing 2 A's among 4 A's. So I have a third equation. I'm going to look at all these possible answers and only one is still valid. And thus I determine the word U uniquely. Okay, so this was an example. And on the general case, what happens? So first we ask for the number of B's or the number of A to determine the one deck. And assume, as in our example, that there are more B's than A's. So we write the word in the same form. So we are putting B's between all the A's. And we are asking questions AB, AAB, AAAB, and so on until U is determined. And you know that we will stop quite quickly because we will stop with M, which is the number of A's. Because if I have more A's in the question than in my word, the answer will be 0. And I have less A's than half of the length of my word. So I have quite few questions. And I can always determine the word from these questions because I'm writing the equations as in the example. And I'm obtaining a triangular system. And here all the coefficients on the diagonal are 1. So I have a unique solution. And it's easy to write this system because you can see that on the first equation, all my coefficients are 1, 1, 1. So this is the first column of the Pascal triangle. On the second equation, my coefficients are 1, 2, 3, and so on. This is the second column of the Pascal triangle. And here I have 1, 3, and so on. So I have the different columns of the Pascal triangle to write my system. Okay, and in the case where there are less B's than A's, that's really easy. I change the word of A and B, and I'm going to ask questions BA, BBA, BBBA in place of AB, AAB, and so on. And this word, it's what we call right bounded block words. In fact, it's just a letter that you repeat and then the other letter one time. Okay, so this is for the binary case. It's pretty easy. And the number of questions, as I told you, is M plus 1 questions. And M is less than the number of occurrences of the letter that is the less present in the word. So there are not so many questions. There are at most half of the length of the word questions. So if I want to determine any word of length 36, I'm enough with 18 questions. Or 19, because there is a plus 1 here. 19 questions. Okay, but now how can I do that for arbitrary finite alphabets? So as the result was pretty easy for binary alphabets, the idea is to reuse it. So we are going to take the projection of the unknown word U on binary subalphabets. So we denote by pi AB the projection of any word over the subalphabet AB. So I just keep the A's, keep the B's, and erase all the other letters. And what I am going to do, I'm going to first try to reconstruct all the binary projections on subalphabets of size 2. This is easy. This is where I'm going to use the algorithm for the binary case. And then I'm going to combine all the projections here to reconstruct the word U uniquely. At least I hope so. I hope that it's always possible. So let's look maybe at an example first. Let's take a word of length 6 over the alphabet ABN. So the first thing to do is to determine the one depth. So I'm going to ask for the number of A's, the number of B's, and deduce the number of N. And now I'm going to look at all the binary sub-alphabets. So first, let's look at the alphabet BN. I'm going to ask questions. So I know that there are less B than N. So I'm going to write my word with B in the middle, as in the binary case. I'm going to ask for the number of BN. The answer is 2. So I know that S2 is 2, S1 is 0. And I determined the projection of U over the subalphabet BN. I do the same for the subalphabet BA. Once again, I have less B's than A's. So I'm writing my projection like that. I'm asking for the number of BA's. I'm determining my two equations. And I have the answer. I know that the projections over the alphabet AB is BAAA. I do the job on the subalphabet NA. There are less N than A's, but here there are 2 N's. So I have 3 unknowns. So I need to ask one more question to determine the solution uniquely. And the projection is ANA, NA. And so I need to use this projection, and this projection to determine U uniquely. So here maybe you guess the solution. The word is banana. But this is a nice example. And the question is it always possible to determine the word in a unique way? So this is the first question. And the second question is that okay, it's interesting, but is it really more efficient than computing the K deck for a value of K that we know that is always sufficient? Okay, so let's look at the first question. Is it always possible to determine a word U uniquely from all its binary projections? And how can you do that? Is there an algorithm? So I need 2 definitions that are a little bit ugly at the first sight, but in fact, if you look directly on an example, they are quite nice. So let's look at an example first. I'm going to define a K marking where K is a sequence of natural numbers and every number is associated to a letter of my alphabet. So KA is 2 here, KB is 3, and KC is 2. So I have a sequence and I have a finite sequence of words. So here I have 2 words. I have U1 and UB. And then a K marking of these words U1 and UB. This is a function that is defined on a part of n square and whose values are natural numbers. And which part of n times n I am going to consider? I'm going to look at couples of pairs ji, where j is 1, 2, because there are 2 words. And for every fixed j, I'm going to look at i's that are going from 1 to the length of the word. So U1 is of length 4. I'm going to look at I, which goes from 1 to 4. U2 is of length 3. I'm going to look at 1, 2, 3. And to every pair ji, I am going to map a number, okay? And there are 2 rules that have to be respected. So the first rule is that if I look at j and I, for example, 1 and 3, I look at U1 third letter, it's an A. So I just copied the words here. So J1, I3, it's an A. And so the number here has to be at most KA. So KA is given here, it's 2. So below A's, I can only put 1 or 2. Below B's, KB is 3, so I can only put B 1, 2, or 3. And below C, I can only put 1 or 2. That's the first rule, this rule. And the second rule says that if I look at a given word and two occurrences of the same letter, so for example, B here and B here, the sequence, so the function, sorry, has to be increasing. So I have 1 and 3. I could have 1 and 2 or 2 and 3, but what's sure is that this value has to be greater than this value, only because I have B and B. I have no link between values of positions where letters are different. And so here I have A and A, so 1 has to be less than 2. So this is a K marking. It's just a function that will, in some sense, associate to every letter of every word U1 and U2 a number. And the second definition is a little bit easier. It's a topological sorting of a directed graph. So if I have a graph, if I want to find a topological sorting, I just want to find a linear ordering of the vertices, such that if I have an edge from a vertex to another vertex, the outgoing vertex has to be smaller for my ordering than the ingoing vertex. So V1 is smaller than V3 for my order. V1 is smaller than V2. V2 is smaller than V6, V4, and V5. Okay, and that's quite direct to see that any directed graph has a topological sorting if and only if it is acyclic. If there is a cycle, you won't be able to find an ordering of the vertices that verifies this condition. And another result that is also direct, is that if your graph is acyclic, so you will find a topological sorting, but this topological sorting is unique if and only if there exists a Hamiltonian path in the graph. So if and only if there exists a path in the graph going through every vertex once. Okay, so now let's combine these two definitions to take a K marking and define its associated graph. So I take the same K marking than before. This is my previous example, and I'm going to define a graph. So which graph? The vertices will be of this form, where I will have a letter of my alphabet and a number, which is from 1 to Ka. So Ka is 2. I have the vertices A1 and A2. Kb is 3. I have the vertices B1, B2, and B3. And Kc is 2, so I have C1 and C2. These are my vertices. Then for the edges, first I'm going to have the edges from a vertex to the vertex with the same letter, and in this, that is the next one. So for example, I have an edge from A1 to A2. I have edges from B1 to B2, and for B2, from B2 to B3. I have an edge from C1 to C2. And the second part is, I'm going to look at all my words and the associated K marking, and I'm going to do the edges as follows. An edge from B1 to C2, this edge. An edge from C2 to A1, this edge. An edge from A1 to B3, this edge. And the same for the second word, an edge from A1 to B1 and an edge for B1 to B2. So this is how I'm going to build a graph associated to a K marking. And this graph will be really useful because we are going to look for topological sorting, and then this topological sorting will allow us to reconstruct words from subwords. So just note that if I have a K marking, the associated graphs does not always admit topological sorting. So for example, this graph has a cycle, and so we just say that if we have a cycle, there is no topological sorting. Okay, and here is the result, the interesting result. So I have some words U1 to UL. I have a sequence K, of integer numbers associated to letters of my alphabet. I say that I can find a word U having all these words as subwords, and what's more, such that for any letter of the alphabet, for any letter A, the number of A in the word is exactly the number of this sequence. If and only if I can find a K marking of these words and a topological sorting of the associated graph. And since we want to reconstruct a word from the projections in a unique way, we would like a condition on the unicity. And here it comes. If I take a particular sequence K, which I call the minimal sequence, the minimal sequence means that for Ka, I have to take the maximal number of A's appearing in all these words. Because if you remember, for the K marking, in a given word, the value have to be increasing for the same letter. So I need at most to have Ka, which is equal to the number of letters in a given word. Otherwise, there won't be any K marking. We will see it on an example just after. So if this K is minimal, if I can find a unique K marking admitting a topological sorting of the associated graph, and if this topological sorting is also unique, then the word U that satisfies this is unique. So I can find a unique word having all these words as subwords and satisfying this condition. But so if I take the minimal values for K, I can find several K markings, but I have to have only one of them that admits a topological sorting. If it is the case, and if this topological sorting is unique, then the word U is unique. This is a sufficient condition. In fact, it is not exactly necessary, but it will be the case in the remaining of the talk. So let's look at an example to be sure that the theorem is well understood. So I still take the same K marking, and this was our associated graph. You remember there was a cycle here, so there is no topological sorting for this graph. But maybe there is another K marking of these words that such that the associated graph is acyclic. In fact, if you just change here B1 into B2, you change these two edges into these two edges. So you break the cycle, and this graph is acyclic and admits a topological sorting. Thus, that means that there exists at least a word U having this word as a subword, this word as a subword, and having 2 occurrences of A, 3 occurrences of B, and 2 occurrences of C. And in fact, here there are a lot of such words. And how is it possible? In fact, this is because there are several topological sortings of this graph, and there are maybe other K markings that also work. But let's look at still the same example with the same words U1 and U2, but let's take the minimal K. So what is the minimal K here? I have 1 occurrence of A, but here I have 2 occurrences of A. So since my function has to be increasing here, Ka has to be at least 2. So the minimal Ka is 2. I have 2 B's in the first word, so my minimal Kb is 2. And I have 1 C, so my minimal Kc is 1. And if I look at all these K markings, I'm obliged to put a 1 below the C. I'm obliged to put B1, B2, and here A1, A2. So I have 4 possibilities, 1 or 2 here that can be combined with 1 or 2 here. So let's look at the 4 possibilities. If I take 1 and 1, I have this associated graph. This graph has a cycle, so it doesn't have any topological sorting. Okay, next K marking, I put the 2 here. The graph changed. It admits a topological sorting. And this topological sorting is unique because you have a Hamiltonian path here. So it means that this graph with this K marking will lead to a unique word U, having U1 and U2 as a subword and having 2 A's, 2 B's, and 1 C. And how can you find the word? You just follow the path B, C, A, B, A. These words work. This word works, sorry. And so let's continue. The third K marking, I put a 2 here and a 1 here. I have another graph, and I still have a topological sorting, which is unique with, since I have a Hamiltonian path. And it gives me another word, A, B, C, A, B, that has U1 and U2 as subwords and 2 A's, 2 B's, and 1 C. And I still have one possible K marking, which has a cycle, so which won't give any word U. So you see that, in fact, I have to consider all the possible K markings with all the possible topological sortings, and every topological sorting will give me a word U that works. But it's possible that several K markings will give me the same word. Okay, and so that's the conclusion of the example. We had 2 K markings admitting topological sortings, and the word U was not unique. We had 2 U's. Okay, so now let's sum up the general case. So I have an alphabet of size Q. And you remember, I wanted to look at all the projections of my unknown word U over binary sub-alphabets. So assume that these words U1 to UL are all these projections. I'm gonna build a K marking of these words. And which K I'm gonna take the minimal K. And what's nice with the binary projection is that if I look at all these projections and a given letter A, either a word does not have any occurrence of A if I do not project on an alphabet containing this letter, or it contains letter A. But if it contains letter A, all the words containing A contain the same number of A. So this KA is minimal, but what's more, it's exactly equal to the number of A in all these words if they contain any A. So because of that, the K marking will be unique. It's really easy. I have to look at all these words and just enumerate the occurrences of any letter and counting it from 1 to the total number of occurrences of the letter. We will see in the example just afterwards. And then the second part is that, okay, I have the K marking, which is unique, but it still remains to verify that the associated graph is acyclic, so admits a topological sorting, and that this topological sorting is unique. And that's a little bit more technical, but that's still possible, and that's still true. So there is a unique topological sorting of the graph. And as in the example, you follow the path, you follow the topological sorting, and it gives you the unique word U. So let's go back at our example banana. We had all the projections B, A, B, and N, and A, and A. What I told you with the minimal K is that if you look at A, here you have 3 A's. Here you don't have any A, and here you have 3 A's. So the minimal KA is 3, and it's reached for every word containing A. You have 1 B and 1 B, and you have 2 N's and 2 N's. So this minimal K is really minimal in some sense. And then the K marking is unique. What are you gonna do? You're gonna, so look at all the A's, there are 3 A's, and my KA is 3. So I'm obliged to put 1, 2, 3. The same here, I'm obliged to put 1, 2, 3. The same for B. B can only be 1. And for N, since the maximal value is 2, I'm obliged to put 1, 2, and 1, 2. So the K marking is unique. And then the associated graph is here. And you have a Hamiltonian path that is giving you the word, the unique word that comes, that has these subwords, and that has 3 A's, 1 B, and 2 N's. Okay, so you have, you know that from the binary projections, you can reconstruct the word uniquely, and you know that, you know the algorithm that does that. Because I didn't mention that, but finding a topological sorting of a graph can be done in linear time, and so the process is quite quick. Okay, and just to finish, how many questions did we ask? So let's take an alphabet of size Q. First, we determined the one deck of the word. And so we ask for every occurrence of the letter except the last one that we can deduce from all the other. So we ask Q minus 1 questions. Then we apply the algorithm on the binary subalphabet. But what we did is that we took the letters first, starting with the letter that occurs the less in the word, and then the second letter occurring the less, so that for every subalphabet, I know which questions I have to ask the minimal number of questions. You know that if I change the order and I put this letter after this one, I will ask more questions. So this is why I order my alphabet. And I have all the subprojections, and as I explained, I deduce the word. So how many questions did I ask? I asked Q minus 1 questions here. And then I looked at all the binary subalphabets, and I asked this number of questions. So for example, letter A sigma 1 appears in Q minus 1 subalphabets. And since it is the less present letter, I will have this number of questions, Q minus 1 times. So this is the first term of the sum. Then the letter A sigma 2 also appears in Q minus 1 subalphabets. But in the first subalphabet A sigma 1, A sigma 2, it won't be used since it's A sigma 1 that will be used. But then it's used in all the other subalphabets. And so this is how you get this number of questions. And the remaining part was to be sure that there are less questions that the K deck for the best known value of K. And we assume that we will only use Linden words. So if we use only Linden words for the K deck, we had to prove that this number is still bigger than our number. And this is the case. This is always true. We were able to prove it in the general case if n is at least k minus 1. But in fact, with a computer, you can check that it's also true for small values of n. So it's always true. But that was quite ugly to show that, and we needed several pages of computations. So I'm going to stop here, and thank you for your attention. If you have any question, feel free to ask.
Are there any questions from Marie? Maybe I will ask one quick question. If you are given a word and a sequence of questions, is it NP hard to determine if those questions uniquely determine the word or not? Or what's the complexity?
That's a good question. In fact, I'm not sure, so I'm afraid to say something wrong. I never considered the question, but that's a good question. So in fact, you know the word you are giving, and you know the questions you are asking.
Yeah.
Okay. That's a good question. Thank you.